This is our Milky Way. Relatively bright, pretty massive, and reasonably easy to spot with a large enough telescope compared to the fainter galaxies. We call them the satellite galaxies that are roaming around Milky Way. These are called the dwarf galaxies or the satellite galaxies. Now take a look on this image from Gaia. So of course we have the Milky Way galactic plane at the center of this image, and around that we have the smaller galaxies. Of course, I'm pretty sure you know the Large and Small Magellanic Cloud, LMC and SMC. Apart from that, we could also spot some other dwarf galaxies well known, Draco and Fornax and others. Now these galaxies are very old. They have way less amount of gas and they have way less amount of visible mass because they are way more smaller than bigger galaxies. And because of this, they are very, very interesting candidates to find dark matter. It's predicted theoretically that the component of dark matter compared to visible matter is way more in a dwarf galaxy or in these types of satellite galaxies compared to bigger galaxies like Milky Way. So that's why finding these dwarf galaxies is extremely important for us astrophysicists to not only to verify cosmological model, but one of the most common model of our whole universe is called this cold dark matter model. According to this cold dark matter model, we should have at least about hundreds of dwarf galaxies around a typical galaxy like Milky Way. But even after tons of efforts, we could only detect about 20, 30, I think maximum probably 40 dwarf galaxies around. I don't remember exactly the number top of my head, but it's definitely not in the zone of hundreds or 200s. That's what is predicted from cold dark matter model. But as you can see, detecting them is problematic because they're very faint. They contain way less amount of stars. Now, this makes things problematic. So we want to detect something, but they are fainter, so we can't really detect them. So of course, there are many digital telescopes, optical telescopes are surveying the sky, ground-based as well as space-based telescopes. But finding them is rather difficult, as I said, because they are so faint. The other problem is that these dwarf galaxies could be buried under the foreground noise that are coming from the starlights of the Milky Way galaxy itself. There is this website called Zooniverse where citizen scientists, amateur astronomers can go and take part in open astronomy projects, and one of them was related to classifying dwarf galaxies. And this is basically not only you see the images of the dwarf galaxy, but you also see a range of diagnostic plots. And your job as a citizen scientist or an amateur astronomer, if you go there, your job would be to predict whether, given this original image and the corresponding diagnostic plots, whether this would be an original dwarf galaxy or not. So basically this becomes like a binary classification problem. Given some diagnostic plots and the original dwarf galaxy image, your job is to basically predict whether this is an indeed a dwarf galaxy or is it some junk or is it some noise. Now this campaign from Zooniverse was actually very huge. Over I think about 1500 amateur astronomers tried to classify about millions of this. Instead of this citizen science program or involving some human beings, a new research paper is actually asking whether we could use a zero-shot scheme using vision language model. We pass these diagnostic plots to the vision language models, and maybe this vision language model under a zero-shot scheme can already predict whether a galaxy is dwarf or not. That is very cool. How do we do this? To find these ghost galaxies or relatively fainter galaxies, we look at these diagnostic plots, and one of the most important diagnostic plot is this isochrone filter. Given the galaxy of a given age and composition, we have expected brightness and colors of stars, and we remove all of the stars that don't follow this isochrone. ISO, same chrome color. And dwarfs mostly consisting of old stars. So our job is basically to keep the stars that follow this isochrone line very closely and remove everything else. Now once we do this isochrone filtering, as you can see on this image, you're left with this central spot, a relatively dense region. Now we know that there is a possibility that there could be a dwarf galaxy. So isochrone filtering is one of the most important things to filter out these foreground stars and focus only on the region of stars that are within this dwarf galaxy. The job for the VLM is essentially this exact thing. As human, what we are doing, we see these 6 images, diagnostic plots with the original image. The VLM, according to this research setup, is doing exactly the same thing. All of these plots are sent to the VLM, and now the job of this VLM model is to predict whether it's dwarf or not. Now, in this research paper, the researchers used GPT-5 Mini as their base VLM. Let's look at this plot, the first important research result plot. This plot looks diagonal. Oh, maybe our problems are solved, because diagonal is great. So this genius AI tool is solving dwarf galaxy classification under zero-shot scheme. Wow, why do we need humans? But that's not so simple. Let's look at the other plot. If you just focus on the left plot, great, the diagonal plot seems like a relatively nice, reliable calibration, but the right plot is telling you a different story. So in this case, what the researchers do is trying to figure out what's happening to the individual dwarf galaxy candidates. So instead of grouping the dwarf galaxies by percentage of positive votes received from human, we focus on individual galaxies, how the VLM is actually classifying every individual galaxies rather than a global summary statistics. We are focusing on individual cases. So now what you are seeing on this right plot is essentially, again, grouping the dwarf galaxies. Whenever you see on the x-axis or y-axis universe, that's basically considering human votes. So group those dwarf galaxy candidates given the percentage of positive votes received from human beings. And it turned out that specifically in the ambiguous regime, so let's say some dwarf galaxy candidates received 50% of votes, positive votes. So basically that's like a conflicting situation, right? So 50% positive votes and 50% negative votes. So human beings themselves, they're very confused whether this is a dwarf galaxy or not. And it turned out that when human beings are actually confused, the VLM is also pretty confused. Specifically, if you focus on this about 30% to 70% positive vote region, the agreement with the human majority drastically drops down, and it basically drops down to about 50%. That is very problematic. And this is highlighted even more in the next plot. What the researchers are trying to do here is they select a candidate of, I think, about 4,000 objects. And to save some computational time, basically the inference cost, they randomly select 4,000 of this dwarf galaxy images and corresponding diagnostic plots. And now to get an estimate on the error, what they do is every of these candidates are passed through the same VLM 10 times. We know that LLMs are essentially having this probabilistic nature, right? So we pass the same candidate images 10 times, and we are trying to gather how many times it's predicting that whether this candidate will be a dwarf or not. So let's say out of 10 times, the LLM says that 4 times it's positive. So that basically means 40% of time the LLM is sure that it's a dwarf galaxy. 60% of the times it's saying that it's negative. Keep that in mind, and now let's look at the plot. So if we now look at the left plot, which is binned by human positive vote fraction, so positive votes, once again, it's essentially whether it's a dwarf galaxy. If the dwarf galaxy is yes, we consider this as a positive vote. So x-axis is essentially been by human positive vote fraction and compare with the VLM test runs. How many times it predicted as dwarf. Now this calibration looks reasonably good. So let's say we pass an object once again, pass through the VLM 7 out of 10 times, it says it's a dwarf. Human votes also are within the same bin. But this we cannot use as a calibration for the VLM, and that is highlighted on the right plot. So on the right plot, what they're saying is that if the VLM is saying that the object is a dwarf galaxy 10 out of 10 times, human positive vote percentage is only about 60%. And for some objects, when the VLM is about 100% sure this is a dwarf galaxy, those objects can receive only at times about 20% positive votes from human. We have this global summary statistics which makes this VLMs looks a genius AI, but when we go individual dwarf galaxy candidates and try to inspect by hand what's going on and then focus specifically on the most complicated ones, the ones that where human beings are also very ambiguous, there the VLM fails. The worst part is that when the VLM is 100% certain, we cannot take that as a high level certain score, because for those candidates, human beings at times have voted only 20% positives. And this tells you that for sure, under this experimental conditions, under this zero-shot scheme, GPT-5 Mini cannot be used as a reliable astronomer friend. Okay, now of course we can go in many different directions. Of course, we have discussed a video on few shot learning scheme with Gemini. So I'm just wondering what would happen if instead of just zero shot scheme, what happens if we could do a few shot learning scheme? What happens if we use updated models? Would this get better or worse? But this is a very interesting research, and of course, if you're interested in this, I will keep the link of this arXiv paper. I guess it's still not published. It was presented in a conference. I'll give the paper link in the description below. And if you're interested in more topics like this, subscribe and we will get back with more. See you. Thank you.